Okay, let's dive into a really big challenge in finding new medicines today. How do you actually sift through, billions of potential drug molecules on a computer to find the ones that might actually work? We're talking about ultra-large virtual screening.
Right, exactly. You've got these enormous digital libraries, sometimes tens, even hundreds of millions of chemical structures.
Wow.
And the goal is to figure out quickly which ones are most likely to stick to a specific target, like a protein involved in some disease.
And the massive hurdle here is the cost, right?
Right.
Screening these libraries the traditional way is just incredibly expensive.
Oh, absolutely. And time consuming. You could be looking at tens of thousands of dollars. Easy.
And potentially years of compute time sort of add it all up.
Yeah, CPU years. It's a huge barrier, especially if you're, say, an academic lab or a smaller research group.
So the source material we're digging into today looks right at this problem. And it proposes, well, a surprisingly simple, computationally light way to tackle it. So our mission here is to unpack how this pretty straightforward approach using basic linear regression, believe it or not,
Mm-hmm.
combined with a strategy called active learning, got these really impressive results. Cutting down costs, but still finding the best drug candidates.
So maybe just quickly, structure-based drug discovery. The basic idea is finding molecules that physically fit, like a key in a lock, with a target biomolecule.
Okay.
Ultra-large library docking just tries to do that simulation computationally for millions and millions of molecules against one target structure.
And it gives each one a score, like how well it might bind.
Yeah, a docking score.
Yeah.
But doing that calculation for every single molecule, that's where the huge cost comes from.
Right. So people have tried to get around this. Active learning, you mentioned.
Yes, active learning. The idea is you don't dock everything at once. You start small,
Okay.
dock an initial small batch, maybe randomly chosen, then you train a machine learning model on just those results
To do what?
to learn to predict the docking scores for all the other molecules you haven't docked yet.
Ah, okay. So it's guessing based on the first batch.
Exactly. Then you use the model's predictions to pick the molecules that it thinks will score best, dock those in the next batch, add the new results to your training data, retrain the model.
And repeat. Sort of iteratively getting smarter.
Precisely. And the common thinking maybe was that you needed pretty complex, powerful ML models for that prediction part, maybe deep learning even.
Which can also be computationally demanding.
Right. But this study, and this is the really fascinating part, found that simple linear regression models,
Wait, like statistics 101 linear regression?
pretty much, that these simple models are remarkably good at accelerating this whole process in that active learning loop.
Okay, that is surprising. What's the practical difference then? Speed.
Huge difference. Training and using one of these linear regression models. Less than a CPU minute.
A minute. Compared to what for the complex ones?
Hours, potentially even a day of compute time for some of the more complex approaches used before.
Yeah, that's incredible. So does it actually work? Did this simple model find the good stuff?
It really did.
Yeah.
In some of their tests, using linear regression active learning, they could retrieve up to 90% of the very best hits the top 1% after docking only 10% of the whole library.
Wow. Okay.
And on a really massive, ultra-large library, they still found 70% of the absolute top-tier hits, the top 0.05%, after screening just 2% of the molecules.
Okay, let me get this straight. Dock a small bit, train a super fast, simple model, use its guesses to pick the next bit to dock,
Right.
repeat.
Hmm.
And by doing that, they found most of the needles in the haystack without even looking at like 90 or even 98% of the hay.
That's the essence of it, yeah.
Yeah.
They also found some interesting details, like smaller batch sizes in each step, say 10,000 molecules tended to work better.
Okay.
And using a simple way to average predictions from models trained at different steps, they call it mean rank ensembling, boosted the results even more, often finding 10–15% more of the top hits.
But I'm still stuck on why the simple model works so well. It feels like it shouldn't be able to capture the complexity. What did the researchers think?
Well, their hypothesis is quite interesting. They basically suggest that the docking simulation itself, especially when done quickly for speed, what they call low sampling depth.
Meaning not spending tons of time getting the perfect simulated pose for each molecule.
Exactly. That initial docking score isn't perfectly precise anyway. It's got some inherent noise or inaccuracy.
Ah, so if the data you're training on, the docking scores, are a bit fuzzy to begin with.
Then maybe throwing a super complex model at it doesn't actually help much more than a simple one. The simple model is good enough to capture the noisy signal.
That makes a certain kind of sense. The complex model might be trying to fit noise.
Sort of, yeah. They even checked how well predicting scores using a second docking run worked, and its value dropped off pretty quickly after the first few rounds of active learning.
Okay, so bringing this back, what's the big implication here for researchers, for you
I
listening?
think the biggest thing is accessibility. This method doesn't demand those super expensive GPU clusters that many labs just don't have access to.
Right.
It dramatically lowers the barrier to entry for doing ultra-large scale virtual screening. It makes it feasible for way more people, more academic groups around the world.
So you're getting results that are, pretty comparable to some of the complex deep learning approaches in terms of finding the best candidates,
Yes.
but it's vastly faster and cheaper to run. It's really about the strategy, the active learning, the small batches, the ensembling, combined with a lightweight tool.
Exactly. It shows that sometimes you don't need the most complex tool in the box. A simpler one, used smartly, can be just as effective, maybe even more so when you factor in cost and speed. It sort of democratizes the process a bit.
So the key takeaway seems to be use the right strategy, like active learning guided by these computationally cheap linear models, and you can smash that bottleneck in ultra-large virtual screening.
Yeah, it makes that critical first step in finding potential drugs much more widely accessible.
Which leads to a final thought, maybe?
Hmm.
If these simple models work well because the underlying docking data is a bit imprecise, what does that really tell us about where the value lies? Is it in getting hyper-accurate scores for a few molecules, or is it more about efficiently exploring the vastness of chemical possibilities to find promising starting points?
That's a great question to ponder. Where should the effort really go, accuracy or exploration?